Okay, this is my second attempt at a problem from MIT 2025 regular season number 3. I had a suggestion in the comments from a Dandep on this one that I do this differently. In the first video, we just evaluated the sum and then the integral, and it was pretty quick. But the suggestion on this one is we switch it up and we do the integral first and then the sum. I think it's going to be quite a bit longer this way, but if you want the fast way, I'll provide a link to that other video in the description. Okay, so to get started with it, right off the bat, we're gonna just switch this. I'm not gonna worry about the convergence right now because we know in the other video it converged, so it converges. So we'll swap these, and when I do that, with respect to the integral, we're integrating with respect to the x. So there's some stuff I can bring out as a constant. Like first of all, I can bring out the n factorial, and then with exponent properties, separating these out, I can bring out 2025 to the n. And then what's left inside the integral is going to be, we're integrating from 0 to 1 over 2025. This part is just going to become x to the n e minus 2025x. Then from here, what I'm going to do with this, you may notice this looks a lot like a Laplace transform, and that's the way I'm going to do it. Not sure if there's other ways, but let's do it as a Laplace transform. We have this problem that the upper bound is not infinity. Well, that's easy to handle. I did a video a while back on the window function. We can do it that way. You can do it different ways. I'm not going to get too into it. I'll provide a link to that video on the window function where it kind of goes through all your different options on this. For this, I'm going to kind of just go and do it and use the formula. So now we've got our formula down here. The intuition on this, it's basically just the unit step function, but we're considering that we could have it on both sides. Now our case is it's simpler really because we're really starting at 0, so we don't necessarily need to do it this way. The intuition on this of expanding this to 0, a window function from a to b, like if we have a point a to b in this function, if it's combining unit step functions that just have a value of 1, what happens is everything outside of this region from a to b gets zeroed out. And that's how we're expanding this to infinity, multiplying in this. We're not changing it because we've done this where we're zeroing out everything outside of a to b. So to make this all work, I need this to be an S to do a Laplace transform. So we're going to call this thing here S, but so we don't forget what we're doing, let's remember that S is going to be just 2025. And so then from here, let's just go ahead and use our formula where the A value is going to be 0 and the B value is going to be 1 over 2025. The first one with 0 is really simple because you could just do it as an integral from 0 to infinity and then subtract off the rest of it. Same thing. So what's going to happen when you plug in 0, you're just going to have a 1 on the first part. Laplace of f of t plus a, but a is 0. So what we have is just the Laplace transform of x to the n. Just use a formula on that. That's going to be n factorial over s to the n plus 1. Then for our next part, we're subtracting off b is 1 over 2025, so we end up with e minus s times s over 2025. And then here we're going to have the Laplace transform of plugging in t plus b now, so we're going to have x plus 1 over 2025 to the n. This is where things start to get messy. I can see space is going to be an issue in this video, so let me see if I can fit some more stuff here at the bottom. Now I'm going to kind of plug back in. We know what our S is, so I'm going to start plugging back in to try to consolidate. So if I plug 2025 in here, what this is going to simplify to is going to be n factorial 2025 to the n plus 1 minus, when you plug 2025 in here, now you just have a minus 1, but it's going to cancel with this. So you're going to have e to the minus 1, or 1 over e, times this Laplace transform here. So let me clean up the board and I'll take this, and all I'm going to do is we'll just plug this back into the blue box there and continue from there. Okay, we're making some progress, but the problem I have now is we need to find a Laplace transform, but of an infinite expression, right? Because it's raised to the n going to infinity, so this isn't that great. But what we can do is just binomial theorem. So let's look at the formula for that. Okay, so we have our formula over here. We're in our problem. Our a value is just going to be 1 over 2025. So when we do that, let's see what we have. So what's going to happen is we're just going to have this infinite polynomial, which is kind of good news because it's easy to get the Laplace transform of a polynomial. Now, one other thing I can do, Let's take this n choose k and write it in terms of factorial. So this is going to be the same thing as n factorial over n minus k factorial times k factorial. And then all we want to do on this is we just need to take the Laplace transform of each of these terms individually. So we're just worried about taking the Laplace transform in here. But the nice thing is it's almost all constant. You know, all this stuff is just a constant right here. And we just need to worry about taking this Laplace transform. So to do this, now let's just call this like f of x. And I'm going to come over here and we just want the Laplace transform of f of x, or just one term. Well, again, the whole constant is going to come out front. So we're going to have n factorial, n minus k factorial, and this whole denominator. Then for this part, we use the formula. It's going to be our input on it's n minus k. So it's going to be n minus k factorial over s to the n plus 1, where we know s is 2025 from earlier. So this is going to end up down here being times 2025 to the n plus 1. And sorry, one mistake, our input on this is not n, it's n minus k. So I need here to plug n minus k into this. It's going to be n minus k plus 1 right here on the exponent. But then we get all kinds of simplification because n minus k factorial is going to cancel. In this right here, same base, so I can multiply these two things together. When we do that, adding exponents, the k's cancel, and this becomes 2025 to the n plus 1. So then just cleaning this up, let's see what we have. This is going to be n factorial over k factorial times 2025 n plus 1. So now we're almost ready to throw this back in the red box. The only thing is, keep in mind this is inside the sum, so really what we need before we plug back in is this whole thing is going to be all these terms from k equals 0 to n. So now we can take this thing right here, throw it back into the red box, and continue. But now at this point we're in pretty good shape. There's a lot of things that are constants. Like within this series, just notice the series is with respect to k. Even though we have n for the upper bounds, this is going to be just a constant here that can come out. And then the same thing with this. There's no k in this. This is also a constant. So anyway, if I multiply in the n factorial, that's going to cancel there and there. And if I multiply in the 2025 to the n, that's going to cancel out the whole exponent and just leave 2025. Same exact thing right here. And then this is gone. And so to clean this all up, now we have, this is 1 over 2025. We still have the 2025 in here, another constant. Let's bring the 1 over 2025s out front of the sum. And then also I'm going to factor out an e in the denominator. So when I do that, inside the sum, this is all gone, but I factored out an e. So in order to make this work, this needs to be an e here. Just noticing if you multiply e times this, you're going to get back 1 over 2025. And then with all the constants out of this, what we're left with is this sum of just 1 over k factorial, and we're going from k equals 0 to n. And then at first I wasn't sure what to do with this, except for the fact that e, we've got the power series for e. We can write e. Let's see, I'm going to use k because I want it to work with this. So I can write e. Let's do it like this. If we have e to the x, we can write this as k from 0 to infinity of x to the n over k factorial. And that mixed variables, this should be a k right here. But then with this, if you just input a 1 into this, you're just going to have e to the 1 or just e. So our sum for e, we can write as the sum. This, if you plug in a 1, the whole numerator just becomes a 1. So now we have 1 over k factorial from 0 to infinity. So I'll plug this back into our sum here, but what I want to do is break it up because I want to work with this. So how I can break this into two pieces is I'll create one going from 0 to n, and then for the rest of it, to get the whole e, I can just add the rest of it, right? So I can create a sum from k equals not n, but n plus 1 because it's finite, because it's discrete. So we're going from n plus 1 to infinity. And then I just need to copy in this part. But the reason for doing that, just so we can get cancellation, right, because this is the same thing as this. So that cancels out. And now we just have a double sum with this thing right here to do. Okay, now to finish it off, we just need to do this double sum. There may be some shortcuts, but I just want to write it out to show how it works. So let's kind of expand it out with some terms. Starting when n equals 1, then the inner sum is going to start at 2. So you're just going to have 1 over 2 factorial plus 1 over 3 factorial on and on to infinity. But then after you iterate through this one, then the next term, n equals 2, well, this now starts at 3. So you're going to have 1 over 3 factorial, all the same stuff, off to infinity. This pattern is just going to keep going on and on and on like this forever. And so after we iterate through this, pretend we iterated through it infinite number of times on each sum, well, you're still just going to have one of these. So adding this all together, this is all adding. We got 1 over 2 factorial, then we got 2 of 1 over 3 factorial, and then we have 3 over 4 factorial, and then you can clearly see the pattern, and this is going on and on to infinity. So it turns out I can just summarize this. We'll still have the constant out front, 2025e. For this sum, what I'm going to do is let's start at 2. So we'll sum from n equals 2 to infinity. And then this whole thing, the denominator is just going to be n factorial, and then in the numerator we've got n minus 1. But this thing's going to be really easy to simplify. What's going to happen, let's just worry about the sum and don't worry about the constant for now. I can break this up into two sums. The first one's going to be n over n factorial, and the second one's going to be minus 1 over n factorial. But on the first one, if I cancel n with n, this thing becomes 1 over n minus 1 factorial. But then here I can just do an index change. I want to get it to look more like this, right? I can add 1 here and subtract 1 here. So that way this here just becomes an n factorial. And then I can bring down this and it's almost the same thing. To put these together, I just want the index to be the same. What I can do is strip out one term. Just plug in n equals 1 here and you're going to get a 1. So I can add a 1 in front and change this index to 2. But that way, all this stuff here, this cancels out, and what we're left with is 1. So this sum right here, this is just 1. So this thing goes away, and for my final solution, we get just 1 over 2025e, and that's it. Okay, thanks again to DanDep for the suggestion. Thanks everyone for watching. Have a good day.